Your RAG agent's lying to you, but not in the way that you think it is. The way it's built is actually wrong, as it's making choices, but it doesn't have the full story. And letting it work without the full story is what separates it from being a toy to a pro system that can actually make you thousands. So I build these systems for real businesses, and in this video, I'm going to give you the 3-step plan to fix it. The 20% of work for 80% of the value. And by the end, you'll stop building toys that you can't trust and start building RAG agents that actually work. So the flaw is actually in traditional RAG itself. It's designed to make decisions with incomplete information. So imagine you're feeding your RAG pipeline a tech manual, like these assembly instructions. And a standard RAG process might take this sentence here, mark the points on the wall where the holes are to be drilled for fastening the base unit. And actually when it's storing it, it might just take that sentence and separate it into multiple chunks that are stored separately with no context. So the first chunk might say, mark the points on the wall. And then the rest of the sentence might be segmented into a separate chunk. So this process of chunking data starts by shredding your documents that you upload into these isolated, meaningless chunks of text. And then when your vector search goes to actually try and find it, all it's got is these fragmented pieces to look for, but it has no idea what the rest of the context should be around it. So it might find the chunk about marking the wall, but have zero context about why we're marking the wall and where we're marking the wall anyway. And this is really difficult to spot, right? Because this is actually a silent failure. It seems to work when you're trying it with simple queries. So if you've tried RAG on simple things, it often works. But then when you're uploading complex documents or significant amount of data, it just completely breaks down and destroys anyone's trust in the system. And the result is ultimately like fragmented context, poor retrieval, and answers that are sounding confident but completely incorrect, which is worse than it just returning something and saying it can't find the right context. So this chain of failure starts right at the beginning of your RAG pipeline in how you ingest your data. Because if you put rubbish into the system, you're obviously going to get rubbish out as well. So most workflows I've seen use this basic text splitter, extract from file. So I'll show you an example of the Netflix earnings report, which is this 84-page document that has multiple headings and lots of hierarchy of information. We've got bullet points in there. Later on in the document, we've got tables here, graphs with context, and more formats, basically a hierarchy of information. And if you put it through this standard extraction technique or the traditional ingestion, extract from file, this is exactly what happens. So we're going to download that Netflix earnings report from Google Drive, put it through the extract from file, and what we'll be able to see is one giant blob of text that ignores all hierarchies. So normally, if we're able to extract it to something like Markdown, we'd be able to see in the formatting what is a header, what's a subheader. But in this giant blob of text, we actually lose all of that context. And we also don't always work with just PDFs, right? We're working with images, we're working with Excel docs. We basically want to work with any format. So instead, we're going to use this improved ingestion, which is using a dedicated parsing tool like Llama Parse, which is all about transforming messy documents into AI-ready data at scale. And that's really important because what we're doing is effectively taking unstructured data or structured data in PDF or image format and actually outputting the results in a format that's ready to be ingested and contain some context about the structure in which it had in the first place. So if we were, for example, to connect this instead to our Llama Cloud account, and all we've got here are a few different HTTP requests, one to the upload document here. But the key thing here is it's super simple because we don't even have to specify the input file type. Llama Parse or Llama Cloud is going to be able to determine that for us. And this is all available on the free plan. You just need to enter your API key as a header auth in here. So what we're basically doing is uploading the document to this parsing endpoint, and we're going to wait and then get the job status and poll that until we can actually get the export itself. So we're polling the job ID in there. And then once we get the export, you're able to see all of the actual formatting structure applied in here. So whenever we've got any tables, we've actually got this Markdown table format, which it might seem like it actually is just a text blob to you as well. But this is now AI ready for ingestion, because actually an LLM can read this structure and understand what fields or what columns and what data sits within each column in a table, for example. And the same with any images, it digests those images and breaks out the structure and text from the images. So we're able to retain the structure of the document, including things like key section headers and subsection headers and bullet points, etc. as well, which is ultimately super important because it retains all the context for when we actually go to try and search that data later. So now the data is ingested correctly with its original context, and you can see some examples of what Llama Parse works with: tech documentation, insurance claim, papers, healthcare forms, invoices, PDFs, and we didn't even have to specify in our upload what document type. It automatically determined that and therefore used the correct parser. So this is the simplest way to do it. You can, of course, use other parsers. However, this is the only one I've seen where you don't have to specify the document type. So it really fits the 80-20 here. And we'll run through another example as well quickly with some lawnmower instruction manual. And you can see that this has a huge content hierarchy where we've got multiple pages, multiple headings, and diagrams, etc. as well. And you can see in the outputs here that we've got the different hashtags for the different levels of header. And we've got all of the information that's been ingested here, including tables and different steps there on instruction pages as well. So that was actually very simple, right? You now have clean, structured markdown that preserves that document hierarchy, but you still have to split that document into chunks to put it into your database. And doing it wrong will just reintroduce that same problem where you have those fragmented vectors with no actual context to go with them. So when we're trying to retrieve them later, it's still going to make no sense and it will pull out incorrect information. And standard chunking methods actually just make this problem worse, to be honest, because they don't at all split documents by meaning. They just arbitrarily split documents by number of characters. So if we to pin all this data here and we feed that into our traditional chunking, what we've got is basically we're defining the markdown content that's being fed in, which is our instruction manuals for the lawnmower. And then we are using this Postgres vector store connecting to a Supabase vector database, and we're inserting those documents into a table named documents_pg_test. And the benefit of using this Postgres node instead of the Supabase node directly is that we don't have to use it with Supabase. We can use it with any vector database that's Postgres there. And it will automatically create a table with this table name. So we don't have to go and set it up in Supabase, for example, but we do need to connect to our credentials. And what we're basically saying is embed or separate that context that's been retrieved into our individual chunks. So if we go into the results of this, we've effectively got all these different chunks. So it's chunked from line 753 to 834. And it's the instruction manual. And this one does end on the end of a sentence. But if we keep reading down these, this one's cut out some random bullet points from the instruction manual. This one's a really short section. While mowing, always wear suitable footwear and long trousers. So if we're trying to retrieve this, if we're asking a specific question, it's going to pull out content that might not be relevant at all. And it's also missing all of the previous context. So it basically means that all the core ideas that are in that context are being artificially separated just by some arbitrary character count, which leads us to this kind of scenario where chunk 1 could depend on chunk 3 or vice versa, but actually they have no context. So the better approach is agentic chunking. Instead of counting characters, it looks for logical breaks, like our paragraphs, our sections, or complete concepts. And it's designed to keep those thoughts completely together. So we can have something that emulates more this style on the right-hand side, where we have some context that's associated with a chunk, but also the chunk itself is a section that is a logical break in whatever document it's receiving. And it's designed that way to keep all of the thoughts together. So let me show you how it actually does that. And we're using this next section, which is the agentic chunking section. And by the way, if you want to access any of this information or more resources on RAG, then I'll leave a link to the community down in the description where we've got all these templates. You can just plug and play, mess around with these here. So if you've never used the LangChain code node before, it's basically just a code node combined with an LLM chain. So we can request specific outputs, but also input a prompt. So you'll see this looks fairly complicated, right? We've got a bunch of JavaScript code to be executed here, all around taking sections and actually chunking them into certain sizes. But also we've input a prompt text. So you are analyzing a document to find the best transition point to split into meaningful sections. So this is the LLM, and this is why it's agentic chunking, because we can actually pass dynamically a prompt with the context on maximum chunk size, as well as the original text to analyze into this LLM or LangChain code node. And what it's going to basically output for us is a chunk that's actually logically broken up. And it's not going to be perfect, but this is significantly better than our general recursive character splitting chunking method, because it recognizes that an entire sentence or an entire paragraph is one complete idea and aims to keep that in a single chunk. And I just want to take a moment here to shout out to Cole Medine, who I actually learned this method from. So definitely check out his channel as well. He's got a ton of great resources on agentic RAG, building out RAG agents, and knows far more than me on this topic. So we've just run it through here, and the LangChain code node basically separates those into relevant chunks and also stores context, which we'll talk about afterwards, and metadata. And you can see this time we've got chunks which are more representative of holistic concepts. So for example, we've got the safety instructions here, which keeps the whole lot of safety instructions in one chunk. And we're basically saying don't exceed a chunk size of 1,000 because it's going to be hard to search through that, but also don't put in one that's less than 400. So the LangChain code just spits out the chunks, and then we're still using this Postgres vector store to actually store those chunks with all the context as well. And the one additional thing we're doing here as well inside this default data loader is giving it certain metadata so that we can come back and identify information around a specific document if we've got multiple documents, but also some context, which we'll talk about afterwards. But we're pulling in here the doc ID, which we're actually just using the doc name from the original Google Drive file here. And that's in case when we pull it later, when we search for it, we need to know what document it came from or need to search a specific document. So metadata stored with the vector is absolutely critical to improving your RAG pipeline. And you can see some of the examples that I've used in a real life use case for internal linking between SEO content blogs. We've stored things like record ID, the article title, the blog ID, the article URL. Once we know the terms that are relevant to internally link to, we're actually going to have to retrieve things like the article URL to apply to the anchor text. So it's really important to store that metadata as well. If you're thinking about the 20% that you need to do, it's splitting documents by meaning, and that's using not the inbuilt traditional chunking method, it's using agentic chunking, which is just using those LLMs to help you split the content based on concepts, which helps you get further away from those fragmented puzzle pieces that you need to bring together. So your data is ingested now correctly, and it's chunked by concept, which is fantastic. This is a really good start, but now you've hit the massive blind spot. The problem isn't just how you search your vector database, it's what you're searching with. You might enter the most perfect query to retrieve a certain bit of information, but a user on the front end is never going to ask a perfect database ready question. They're probably going to ask something terrible, like how do I fix my broken workflow? And it's a terrible search query because it actually has no specific keywords, and the vector search has no idea what to do with the words broken workflow. Even though it's searching for semantically relevant terms, it still might struggle with this and therefore struggle to retrieve the actual answer. And the actual answer might be stored, for example, in the database as something like troubleshooting instructions. And with this search query, you might never find it unless you get lucky. So this is where query expansion comes in, and we're using an AI agent to do this. And it's a really well-known concept, but not very well utilized. And it's basically supercharging with an LLM your classic query. So say we input that query, how do I fix my broken workflow? What it's going to do is just think about 3 hypothetical search queries that are optimized for a vector database search focused on keywords and semantically relevant queries. And it might come out with something like N8N Workflow Troubleshooting Guide, how to debug N8N workflow errors, common N8N workflow execution failures. So you can see how those are much more optimized versus that one query. Plus, we're actually giving it 3 chances to go and find the right context. So think of this as like a query rewriter that actually outputs multiple times. So we'll open up the chat window and we'll do safety instructions. And if we just hide that window and see what exactly comes out in this query expansion, it's general safety instructions guide, essential safety tips and precautions, or common safety measures and protocols. So it's taken my rubbish query and actually expanded that. So this is query expansion. So then query expansion's fired into our AI agent, which is going to search the vector database. And that's going to come back with a ton of results. So for example, we've set in our Postgres vector store here to return from the lawnmower table, which we're using as an example, to return 25 chunks, which is actually a significant amount. Now we're doing this 3 times because we've got 3 queries, so we're returning 75 chunks. And effectively what we're doing there is putting the 75 chunks back into our AI agent, which might sound great, but actually it's stuffing them all into the LLM prompt. And you'll know if this is a problem if you've ever written a long, comprehensive prompt and the prompt hasn't followed the instructions you actually want it to. It's because it often gets confused with all of the context that it's got. It doesn't know what to prioritize. And the same is going to happen here. It's also a recipe for high costs because we're putting so many LLM tokens in every single query we make. And it's not even going to be able to find your question because your question is going to be inserted right at the very end underneath all the chunks and the context from those chunks, which comes to the second fix for this, which is called a re-ranker. And I only found out about this recently, but it's incredibly powerful. And we're using a specialized, lightweight, cheap model from Cohere, and you can go to cohere.com to read more about their products, but you just need an API key. You can get an account completely for free to test this out. And the way you can imagine this is, imagine you're in a car parking lot and you're comparing 2 cars that are next to each other. Cosine similarity is basically saying if those cars are facing the same way, they're similar, or they are the same car nearly. And if they're facing opposite ways, they're not similar, which we know is not a very accurate way to perceive things. But re-ranking is like having a friend there who listens to the kind of car that you want, i.e. our original query, and then looks at all of the cars and finds the one that matches your words and needs the best, not just one that's facing the same direction. So it basically does one job extremely well. It takes your large sets of results and reorders them. So you pass in the 25 chunks, or the 75 in this case, and it returns only the top N, or top 4 in this case, using its lightweight model. So it's basically saying, out of the 25 chunks I've received, these are the ones that you should pass into your LLM context. And it means that your prompt becomes much cleaner because actually the context that's being passed back in every time are just 4 chunks and not 25. So it can actually find your query under all of that information. So just using a re-ranker is one of the most powerful things you can do to improve your RAG responses because it's giving the LLM only the most signal-rich information to give the right answer. And then there's one more thing to be said about giving your LLM the full story. And this is the final and most important step that ties everything together. After your re-ranker identifies the single best chunk or the 4 best chunks that are most likely to give a good answer, the biggest mistake you can make at that point is actually just sending that chunk to the LLM. Because if you remember our diagram earlier, we might have a great chunk because we've actually put as much context into that chunk as possible, but we still don't have that chunk context that surrounds it and comes with it. And therefore, we don't have the full story to make an informed decision, or our agent doesn't have the full story because it doesn't have all the context surrounding that. So you can actually use a few different strategies for this, right? And it's called context expansion. So there are multiple ways you can do this, right? One's neighbor expansion, which is pulling before and after. The other is full document ingestion. Now, with the types of documents that we're using, they are 30 plus page documents often. We're not going to pull the full context of the document inside there because we're actually going to spend a lot more money on the LLM token usage by doing so. So we're going to opt for the neighbor expansion technique, which will be really good in most use cases, which is actually just giving it enough context so that it can review the information that just came before it, the information that came after it. Now, you can over-engineer and make this really specific to pull exact sections, but what we're going to do is just try and do the 20% that gives us the 80% of the results, right? So what we're actually doing, and what we didn't show you earlier, is inside this LangChain code node, we've extended the logic here to actually output things like the chunk size, the chunk number, the content that comes after it, i.e. the chunk that comes after it and the chunk that comes before it. But not only that, some additional summary information around that context, so that when we actually output any chunk inside here, we can see all of this information in the JSON. So it's got no chunk before because this was the first chunk we pulled, chunk number 1. But after, it says may result in electric shock, fire, and/or serious injury, which we can see was the chunk from afterwards. And then in the summary, it's also given us this additional context. Read all safety instructions and warnings before assembling and using your petrol lawnmower. So that is what this text chunk is about, basically. It's taken that text chunk and it's used an LLM to say, summarize what this is about and apply that as context. And what that means is when we upload or ingest our data in the earlier stages, we've actually uploaded all this additional context in our metadata, the chunk number, the context before, the context after, and the context summary, so that when we do actually come to retrieve the information, we not only have the semantic search from the vectors that pulls back the most relevant information, then we rank those chunks using the re-ranker. We apply one final layer, which is actually bringing in all the additional context from before and after that chunk to give the LLM that we're using the best chance to give us the most precise answer with the information it's got. And we can see that in action when we go back to the chat window. We run our query for safety instructions through, and actually it's then able to apply all those 3 layers to find the right information from the document and actually return that to us. And we can see here are the consolidated safety instructions extracted from the provided manual text. Follow these every time you assemble, operate, transport, maintain, or store the lawnmower. And it's got a bunch of information that it's pulled exactly from that query. And that's a combination of everything we've done so far in the ingestion phase, the query expansion, the re-ranking, and then actually consolidating all of that context to give us the best chance of finding the right context to give us an accurate answer. So hopefully you can see how powerful that is. And you've completed now the 3-step blueprint for our advanced RAG agent. So you've seen all these distinct components, and now they need to be connected into that robust pipeline for your RAG agent. And as you know, this is exactly the kind of challenge that workflow automation is designed to solve, and that's why we're using N8N. But before you can assemble complex systems like this, you need to be fluent in the core building blocks that you'll be using. And that's why in this next video, we're going to focus on the 80-20, and I'm going to show you the 13 most essential nodes within N8N that you'll need to master for building advanced AI systems like the one we just designed.